Hey guys, welcome. Today we will start a new chapter, chapter number 4, which will concern some additional applications of derivatives. And in this chapter, you'll see something a little bit different than you have seen in the last chapter. You'll see more qualitative properties of the derivatives. And when I say this, I'm referring about extreme values of functions. I'm talking about the mean value theorem or something related to this. I'm talking about zeros of functions, which will relate to derivative, or also we'll be talking about the curve sketching with asymptotes, also about the graph, how to use the derivatives to sketch the graph of a function, and also towards the end, I will be showing you another method to deal with limits of functions. And that method, you'll see it's very effective. It's called L'Hopital rule. And well, last but not least, why not? We'll be talking about some applications. In fact, I will be dwelling more on optimization in physical sciences, engineering, economics, and so on. All right, so today, I would like to start with something which will be very important. And we'll be talking about, as you can see in the title, we'll be talking about, let's write it, extreme values and mean value theorem. Well, this will be maybe a bit longer, the lecture, but these notions will be very important. And first, I would like to start with extreme values of a continuous function. Well, you do remember one thing. At some point, when you know that the continuous functions have the so-called intermediate value property. So when you have a continuous function that takes the negative values and jumps to positive values, it has to go through zero. So that's what you need to know about continuous function. So, okay, now. So let's consider, let f be a function, and this function is defined, right? So it's a function defined on an interval I, that contains this number contains the number x naught, let's say. So we have a function, and we have this point x naught, let's write it here, is in this interval I. So that's what we know. Then we have the following. F of x naught, so in fact, let me write this with a different color. Then f of x naught is absolute maximum right of f of the function f on let's say on a domain D, right? If we have this inequality, f of x is greater or equal than f of x naught for all x in D, right? So that's what we, and also f of x naught, as you can imagine, is absolute minimum of f on D, right, if the reverse inequality holds true. So if f of x is less or equal than f of x naught for all x in D, right? So that's the definition of an absolute min and an absolute max of a function. And now let me point out a remark here. Well, we can say that the absolute min, so the absolute minimum and maximum, right, of a function f on the interval I, right, are called the extreme values or absolute value of functions, or absolute extrema of functions are called extreme values right? Or we can call them absolute extrema. Okay. And now let me give you some examples. So let me start with the first example. So example 1. So I want you to look again at the definition. So these are the two definitions for absolute max and absolute min. And now let me give you an example. I'm going to draw the graph of a function. So let me give you this example. So let me draw the following graph. So these are the axes, x, y, right? And I suppose I have a function here that goes like this. Well, you can imagine what function this is. So this is the graph of this function g of x. And let's just say we have a point here, 1. And here again, 1. So this is the point of intersection 1, 1. Well, as you can see in this graph, clearly g of x has neither a maximum or a minimum. Or minimum. Okay. Well, simply is, to put it this way, simply is not possible to find a minimum or a maximum y value, as you can clearly see. So we cannot find a minimum or a maximum or a maximum y value. Okay, so let me give you another example. Example number 2. So let's say example 2. Let me consider this piecewise function. So let h of x be this function. So I'm going to consider this piecewise function. Let's say on this piece, on this branch, it's the quadratic function, the simplest quadratic function, x squared. So if x is non-zero and is 1 if x is 0. All right, so this is a function. And we're asked to find the minimum and maximum on the interval negative 1, 1. Right, okay. Now let's draw this function. So the graph of this will be a parabola, so let's be careful here a bit. So the graph will be something like, let me point out this one here, this one here. So it will be something like this. Okay. Okay, this, actually the drawing is bad. Let me draw it again. Okay, that's more like it. Right, and here I have, let's say, so it keeps going like this. Here, let's say I have this point. So as you can see, if you look at this function, the minimum, well, it should have been 0, but at 0 it's 1, so there is no minimum. So there is no minimum. But the maximum is 1. Right? As you can clearly see it on the picture, right? All right. Well, now let's talk about, well, as you have seen these two examples, but now I want to put some theory. I want you to see exactly what this is, where this comes from. And the first theorem that I would like to cover is the following. It's theorem, let's say 1. So the first theorem, which we will call this extreme value theorem. And it says the following, right? So it says that a function f has both an absolute maximum and an absolute minimum, right, on a closed and bounded interval. This is important. Closed and bounded interval. Right, where this function is continuous. So where it is, and this is an important thing, where it is continuous. All right. In other words, this is actually also called Weierstrass theorem. It belongs to this German mathematician Karl Weierstrass, which is nicknamed the Prince of Mathematical Analysis. So this goes back in the 1800s, actually, or 1700s. No, actually 1800s, sorry. Basically says that if you have a continuous function, then this continuous function is bounded, and moreover, the bounds are attained. In other words, you'll have a min and a max, and those values are attained as well. Anyway, okay, now I would like to talk about relative maximum and relative minimum. So relative, because I would like you to distinguish between the two. What is an absolute max? What is the relative max or min? What is the local max, local min, and so on. So relative maximum. It's very important to distinguish between these. So a function, right? Now we have seen what it means for a function to be an absolute max, an absolute min. Now we'd like to see what what it means for a function to have an absolute relative max or a relative min. So a function f is said to be sorry, it says said to have, not to be, a relative max relative maximum right at a point, let's say again, let's take x naught, if so relative max if f of x right is less or equal than f of x naught right for all, and this is important here, for all x, and I'm gonna say this explicitly because it's important, for all x in an open interval containing x naught, in an open interval containing x naught. This is important, a very important piece of information, because you now in this way you can distinguish what it means to be a relative max. You can distinguish between a relative max and an absolute maximum, right? If we go back to the definition of the absolute max, you see that the same inequality holds true, but for all x in that domain D. So it's not just an open interval containing x naught. Well, as you can imagine, the same scenario will hold true for when we deal with the relative minimum right? So a function f is said to have a relative minimum right at a point x naught if, well, the reverse inequality holds true. So let's say f of x is greater or equal than f of x naught for all x. Maybe I should put here, okay, put the same point, but you can put any, something else. Anyway, it doesn't really matter. For all x, and again, the same thing in an open interval containing x naught. Right? So I want you to look at the definition of these two definitions. And now, well, combining these two together, I would like to say what it means for a function to have relative extrema. And well, you can collect these two and you can say that relative minimum, or we can say relative minima and relative maxima. Well, we'll call this, is called relative, let's say this, relative extrema. So when you talk about relative extrema, you talk about relative min and relative max. So this is important. All right. Now, I would like to say a few words about critical number and critical point. So critical number, and also critical point. Now, suppose f is defined. So we have a function f, which is defined at x naught. So, and either f prime of x naught is 0, right? Or f prime of x naught does not exist. Okay. Then the number, this number x naught, is called critical number of f. Is called a critical number right? We'll call this a critical number of f. And this point, when you represent graphically of coordinates x naught, f of x naught, on the graph of f, is called a critical point. It's called a critical point. Right, so these are the definitions for critical number and a critical point. And now let me draw a figure. I would like to draw the graph of a function, and you will see on the graph which one is you'll see the critical points, and you will see which one is an absolute min, an absolute max, and so on, and which one is a relative min and relative max. So let me draw the following picture, because I think it's better to illustrate this graphically. I think you can understand it much better this way. And let's just say here we have this interval a, b, right? And at this point here, we have this point here, and just so the graph will go like this, goes like this, goes like this, then like this, and then goes here. All right, we'll just say here we have another point. So here we have some points. Again, here I have a point, and here I have a point. And then let's say here I have a point. Now let's just say here it's a point of coordinates x naught, f of x naught. Okay, let's just say here it's points of coordinates x naught, f of x1, let's say. Here I'll have x naught prime, f of x naught prime, right? Here, let's just say I have x2 and f of x2, and then that's it. Okay. So by looking at the graph of this, by just looking at it, oh, well, what can we say about it? You see, if we look at it, we can say that some of them are relative maxima, but not absolute maxima. But if you look at this, you can say that this guy here is the absolute minimum point. Right? And if we look here on the highest point on the graph of the function is this guy. So we'll look at this guy as, so this guy here is the absolute maximum point. Right? And now we can look at this, these 2 points here. One of them will be the relative maxima, and the other one will be relative minima. So this guy is the relative maxima. Right? On the interval AB. Right? And this guy here is nothing else than just the relative minima. In fact, f of, okay, relative minima on the interval AB. So this is what you need to know. Well, clearly, now I think the picture is quite clear, right? So this is how you graphically interpret the absolute. This is how you distinguish between these two, how you distinguish between the absolute min, max, or and relative min and max, right? Okay, now let's see some examples. We'd like to see some explicit examples how to operate with this. And I think this will be example number 3. Anyway, I'll just call it an exercise. I'm not going to number it from now on. So now what we would like to see is to find the critical numbers for the function f of x equals 4x cubed minus 5x squared minus 8x plus 20. So we would like to find the critical numbers, right, for this function. As you can see, it's a function of as a polynomial function of degree 3. Well, clearly, if you look at this function, this is defined for all real values of x, right? So we can say that f is defined on R with real values. And now let's just take the derivative. And by doing so, we have that f prime of x will be nothing else than just 12x squared minus 10x minus 8. Of course, the derivative will always be a quadratic function, right? The degree of the function will decrease. Well, and clearly this guy is also a polynomial, just like I said. So f prime is also defined for all, so the derivative will be defined for all real values of x. Okay, and now what we're going to do is to solve this equation. So we solve the equation because this is how we will find the critical numbers. F prime of x equals 0. So this is what you need to know. So f prime of x equals 0. And we will have the following. So this would be 12x squared minus 10x minus 8 will be 0. Or if you, well, this is a quadratic equation, you can solve it any way you want. This will be equivalent. Well, you can just factor some numbers here, maybe can factor 2, so this will be nothing else than just 6x squared minus 5x minus 4 equals 0. Well, again, this is a quadratic equation, and by solving this, we'll get the solutions by solving this. And I'll leave this to you. So we get the solutions. X1 equals 4 over 3, and x2 will be negative 1/2. And I'll leave this to you as an exercise to solve this, right? This is just basic college algebra, so I'm sure you can do it. Okay, all right. So we will call these numbers, so the critical numbers are x1, so let's put them here, 4 over 3, and x2 is negative 1/2. So these are the critical numbers. And now we would like to find the critical points. So the critical points will be given by the following. So we will evaluate f at 4 over 3. And by doing so, oh my, so we'll have 4 times 4 over 3 cubed minus 5 times 4 over 3 squared minus 8 times 4 over 3 plus 20. And this guy here will give us, if we do all these computations at some point, and I'm just gonna say it directly, this would be 288 over 27, right? Okay, and now we have to also, and we can also evaluate f at negative 1/2, which will be 4 times negative 1/2 cubed minus 5 times negative 1/2 squared minus 8 times negative 1/2 plus 20. And at some point, after some computations, this would give us 89 over 4. So finally, to summarize all this, we obtain that the critical numbers are, let's say, x1 is negative 1/2. I think I call this, okay, sorry, it's 4 over 3, and then and x2 is negative 1/2. And the critical points are, let's say, P1, the first point of coordinate 4 over 3 and 288 over 27. And the second point, P2, will be of coordinates negative 1/2, 89 over 4. Okay, and that's it. So this is the first example that I wanted to show you, right? So let's just now let me give you another example. So exercise. Okay, I'm not going to number it. Well, the same thing. So find the critical points and the critical numbers. For the following function, for f of x, and I'm going to take a rational function this time. So this would be e to the x over x minus 2. And of course, we have to avoid values for which the denominator is 0. So in other words, we will avoid the values for each x equals 2. So this will be defined on the real line, and I'm going to exclude the value 2 and real value. All right, so this is what I want to solve. Okay, let's see. So how are we going to solve this one? Well, as you have seen on the in the previous example, in the previous exercise, we just take this function, we compute the derivative, and then we set it equal to 0, and then we just do the algebra. All right. Let's do that. So we have that the derivative f prime of x is, well, as you can see, f of x is the quotient of two functions. So let me write it in this way. So this would be, so here we will apply the quotient rule. And this will give us e to the x prime times x minus 2 minus e to the x times x minus 2 prime, everything over x minus 2 squared, right? Where we apply the quotient rule here. And now, once we do the computations here, so this would give us e to the x times x minus 2 minus e to the x minus e to the x times 1. Everything over x minus 2, everything squared. And this would give us, this would be equal to, we can factor e to the x here, so it will be e to the x times x minus 3, everything over x minus 2 squared. Well, we know that the derivative is also, so let me write this, note that the derivative, so that f prime of x is not defined at x equals 2. Right? But also not defined, right? Is not defined at x equals 2. So this x equals 2 is not a critical number. So x equals 2 is not a critical number. Okay, that's great. So if we set up, so the equation, because we would like to solve this equation f prime of x equals 0. So the equation f prime of x equals 0 implies that x equals 3, right? As you can see here, if you look at this guy, so this guy has to be equal to 0, right? So the only option we have is for x to be 3. Okay, that's great. So now this will be the only critical number. And now when we evaluate the function at x equals 3, we have f of 3 is e cubed. So the critical point is, let's say, p of coordinates 3 and e cubed. And that's it, right? Pretty straightforward, I would say, right? Well, in my notes, if I look in my notes here, right, there is another example. Well, in fact, there are two other examples. So there is, in fact, let me do one of them. Let me do one more exercise. Let me do one more example. Let's just say we have this function. So find the critical numbers and critical points for this function, for f of x is x minus 1 squared times x plus 2. Okay. So we would like to do the same, apply the same procedure, but this time for this function. As you can see, if you look at this function, this is the product of two functions. So when we will take the derivative here, guess what? You will apply the product rule. So f of x is defined for all real values of x, right? Since this is a polynomial, probably it's a polynomial of degree 3. So we have that f prime of x is, let me write it in this way, it's x minus 1 squared times x plus 2, everything prime, so the derivative of this guy. And this guy, when we apply the product rule, this will be x minus 1 squared prime, let me put it this way, times x plus 2 plus x minus 1 squared times x plus 2 prime. And this will be equal to, if you look at it, if you look at this, right? So you can even expand, or you can apply the quotient rule there. Anyway, so it will be 2x minus 2, right? Times x plus 2 plus x minus 1 squared times 1, right? So that's it. All right. Now you can factor here, so it's 2 times x minus 1 times x plus 2 plus x minus 1 squared equal well, we can factor x minus 1, so equal is x minus 1 times 2 times x plus 2 plus x minus 1. Or if you want, this will be nothing else than just, so it will be 3x. So this would be, yes, 3x plus 3. So in the end, this will give us 3 times x minus 1 times x plus 1. So this is the derivative of f. As you can see, is defined for all values x, all real values of x, right? And now, guess what? We will solve the equation. So the equation f prime of x equals 0. So this equation, which will be equivalent with 3 times x minus 1 times x plus 1 equals 0. So this equation has solutions. So the solutions of this equation are x1 equals -1 and x2 is 1. So in other words, this will be the critical numbers. And now, so these two guys here, we'll call these the critical numbers. And the critical points, so the critical points are given by, let's say, P1 of coordinates, well, f of -1 will be 4, So it will be -1 and 4, and P2, f of 1 will be 0. So it will be 1 and 0. So these are the critical points on the function, on the graph of the function f. Well, okay. Now let me talk about something else. I think there is in my notes there is another example. Yeah, there is another example, so you can look up in my notes for more examples of this type. But I think you got the picture at this point. So there is no point for me to lose any more time with more examples, since I think 3 of them is more than enough. Now, let me talk about absolute extrema. All right, so how we would like to see how to find absolute extrema of a continuous function defined on a closed and bounded interval AB. So the question we would like to address, how do we find absolute extrema of a continuous function on an interval. And like I said, this interval will be closed and bounded interval AB. So this is the question we would like to address and would like to answer. And the short answer is the following. So there are some steps to follow. Step 1. Well, we compute the derivative of f. So compute f prime of x, right? And find all critical numbers of f on AB, right? So that's step 1. Step 2, we evaluate f of x at the endpoints A and B. This is important. On each critical number x naught, let's say. In fact, let me stress this because it's important. And now step 3. We compare these values. So compare the values in step 2. So we'll compare them in the following way. So the largest value is the absolute maximum of f, is the absolute maximum of f on the interval AB, right? And the smallest value is the absolute minimum of f. Absolute minimum of f on the interval AB. Okay, so these are the 3 steps that you need to remember. Well, it's kind of obvious. Well, remember we had that picture before. Let me go back to it. The picture, I think it was, you see, look at this picture here. That's the picture I'm talking about, as you can see. So keep this picture in mind. You have an absolute max, an absolute min, a relative max, a relative min. See, we have absolute extrema and relative extrema. Okay. Now let me give you an example. I want you to see on how this works. This algorithm, let's say, will work on a on an example. So example, and let me consider the following function. Let's just say, well, I like to find the absolute extrema of the function of the following function. And well, we'll consider like a degree 4 polynomial function. Let's say x to the 4 minus 2x squared plus 3. And we will define this. So on the interval, -1, 2. Again, well, as we suggested in our, you see here, in our algorithm, the first thing we need to do is just to compute the derivative of f and to find all critical numbers of f on that interval. And then in step 2, we'll evaluate f at those critical numbers that we found. And then also we will evaluate the function f at its endpoints. And then we'll decide which one is bigger, which one is larger. So that's pretty much it. That's basically what this is all about. All right, let's do it. But first, very first thing, we can compute the derivative. So we have that the derivative, we have that f prime of x. So this guy is 4x cubed minus 4x. And we can factor here, we can factor even 4x, so it will be 4x times x squared minus, so it's x minus 1 times x plus 1. Okay. And now the critical numbers are given by well, so let me say here f prime of x equals 0 has solutions. In fact, let me write it and then has solutions x equals 0, x equals 1, and x equals -1. So these are the solutions, and in fact, we will call this directly, or we'll call these 3 the critical numbers. And now let's evaluate. So we evaluate f of 0, which will be 3, f of 1, which is 2, f of -1, which is 2 again, and f of 2, right, because it's on the interval of -1, 2. So f of 2, which will be 11. And now let's look which one is the largest, which one is the, as you can see, I have 2. So maximum of f of x is when it's 11. So we'll call this absolute maximum. And when and the minimum of f of x is when it's equal to 2, so we call this the absolute minimum. And as you can see, this absolute minimum is attained for two values, for 1 and -1, right? Just look at them here. So these two guys, so that's minimum, absolute minimum, and this is absolute maximum, right? Okay. There are some other examples in my notes now that I look. Well, let me just take their another example. So this. So the other example I have in mind is the following. Let me just take a trigonometric function. It will be a little bit more complicated. Let's just say, let me denote this from by t of x by trigonometric. So this would be, let's say, 1/2 times sine squared of x plus cosine of x plus 2 sine of x minus x. And let's just say we would like to see this on the interval. Okay, so t, so let's say on the interval 0 and pi over 2. So we would like to find critical numbers. The absolute extrema, sorry. Find the absolute extrema of t. So we'd like to find the absolute extrema of the function t of x. Well, again, the same thing. So we would like to compute the derivative. So we have, let's do that. T prime of x is 1/2 times, this will be 2 sine of x cosine of x minus sine of x plus 2 cosine of x minus 1. And once we do some computations here, this will give us, let's say 2 cosine of x minus 1 times, and this guy here, we can factor sine of x, so it will be, at some point, this will give us sine of x plus 2, everything over 2. Okay. So this is the derivative, and now we solve the equation. So the equation t prime of x equals 0 has solutions. And let's be careful here. So once we have to code this part here, this guy to be equal to 0. And on the other hand, we have this guy here equal to 0. So this will imply that this will have the solutions. So from the first one will be x equals pi over 3. And with the second one, we will have that sine of x plus 2 equals 0. But as you know, that sine of x cannot be -2 because sine is bounded between -1 and 1. So that's the only solution we have. So this is the only one. All right, so this is the critical number. Let's write it here. So this is the only critical number. Okay. And now let's evaluate this function at the x equals pi over 3. So let's do that. So we evaluate. T of pi over 3. And once we do this, this will give us, it will be 1/2, 3/4 minus plus 1/2, sorry. Plus 2 times sine square root of 3 over 2 minus pi over 3. I hope I didn't do any mistake. Well, it's the same in my notes as well. Okay, so we have this. And this would give us, if we do some computations here, it's 5/8 plus square root of 3 minus pi/3. And approximately this would be, if we put in some calculator, 5/8 plus, so approximately this would be 0.93. All right. Also, we evaluate the function t at its endpoints. Remember that this function is defined on the interval 0 pi/2. So we will evaluate t of 0 and t of pi/2. So t of 0 is clearly 1/2. And t of pi/2, if you plug it in, it will be, I think I made a mistake here. No, this is not, this is 1.31, something like this, yeah. And t of pi/2 will be what? Will be 5/2 minus pi/2. And this guy, I believe, when you do the put it on the calculator, just give me 1 second. Okay, all right, and this will be indeed 0.93, and that's it. And now we'll have to decide which one is the absolute min, which one is the absolute max. Well, as you can see, this value here is the largest, right? So this will be the absolute max. And wait, T0. And this guy is the absolute min. Okay. All right. So this is how we solve the problem. Well, it's pretty straightforward. But now let me give you another example. I would like to do another example, which will involve some physics here. So example. A particle moves along the x-axis and position at time t, right? And the way it moves is the motion is described by this function. S of t is t to the 4th minus 8t cubed plus 18t squared plus 60t minus 8. Okay. And let's just say that this function is defined on this interval from 1 to 5, closed interval, right? So this is how the particle moves along the x-axis, right? All right, and now we will like to find the largest and the smallest velocities. Okay, well, it's quite clear. When we will talk about velocity, we will look here. We have this word velocity. So when we talk about velocity, we talk about the derivative of the position function, right? S of t. So again, the velocity. So the velocity, and let's call this v of t, is given by, as you know, v of t is nothing else than just the derivative of the position function. So it will be the derivative of this, which will give us 4t squared minus 24t, 4t cubed minus 24t t squared plus 36t plus 60. Okay, so that's the derivative, right? All right. Well, and now we would like to find the absolute extrema. So pay attention here, because we're finding the absolute, the largest and the smallest velocity, right? So in other words, we need to take the derivative again of the velocity and set it equal to 0. So now v prime of t, so once again, if we take the derivative, this will be nothing else than 12t squared minus 48t plus 36. And we solve the equation v prime of t equals 0, right? So we want to solve this equation. All right, let's see, which is equivalent with, and let me put it this way, with 12t squared minus 48t plus 36 equals 0. Okay, we can factor 12 here. So this would be equivalent with 12 times t minus 3 times t minus 1. So this will imply that t equals 3 and t equals 1. So these will be what we will call the critical numbers. So these two guys are the critical numbers. All right. And now what we would like to do, we would like to evaluate our function v. Pay attention, because we have not s, because we're interested in velocity, and the velocity is the derivative of s. So we would like to evaluate v at these 2 points at the critical numbers, but also at the endpoints of our intervals, which are 1 and 5. So we would like to evaluate v of 1, v of 3, and v of 5. So v of 1 will be 4 minus 24 plus 36 plus 60, which will be 76. All right. Then v of 3. Once we evaluate this, this will give us, in fact, let me just, I don't want to do the computation. So this will be 60. I'll leave them to you as an exercise to figure it out. And then v of 5 will be nothing else than just 140. Okay, so we have these numbers. And as you can see here, the maximum velocity, so there's this given by this guy. And now if we want to look at the minimum velocity, will be this guy. Okay, that's beautiful. And that's basically the end of the problem, right? So we're asked about the largest and the smallest velocity. All right, now I would like to give another example, a real world example. And this time we'll talk about a box. And the statement is the following. So a box with a square base is constructed so that the length of one of the sides, the length of one side of the base plus and I'm going to write it here, right? The height is 10 inches. Okay, and now we're asked what is the largest possible volume of such a box. All right, let's look at this little guy here. Well, let's identify some keywords here. So a box, so we have a box, and this box has a square base. So we know what the base is, it's a square. And we know that the length of one of the sides of the base plus the height is 10 inches. Okay, I think we have all the information right now. Basically, let's just draw a picture first. Right. Let me just draw this box. Oh, it's like a cube. Okay, let me just draw it better. I'm not extremely talented with these kind of things, but anyway. Okay. Okay. So we have this box. And now the base is a square. So keep in mind this is B and B, let's say. So they're equal, right? This is a right angle triangle here and here as well, here. And this is the height, H. So all of them, all the heights are the same. So the B, right? Okay. So now what we're going to do, the side of the base, like I said, so this side of the base will denote this by B. And the height of the box is denoted by H. And now let's look at the problem again. So we're given that, so we are given that B plus H is 10, right? So we're given this. So from here, this implies that H is nothing else than 10 minus B. All right, let's keep this in mind. And now the endpoints, so the endpoints, of course, are, so B is between 0 and 10. And now we'll see, we're asked about this guy here, about the volume of such a box. So this word volume. So we need a formula for the volume of this box. And let me write it here. So the volume of the box in this case is B squared times H. All right, at this point, this is a mathematical problem. In other words, we need to find, so V, this function V, which will be in terms of, so let's call this V, okay, let me write it in this way. So V is the volume of the box, and as you can see, it's B squared times H, but I want to have this as a one variable function. So what I'm going to do, I'm just going to replace this in here. So this will be B squared times 10 minus B. So at this point, this volume is, this function V is of variable, V is of variable B, as you can see, right? Okay. All right. So I have this function. So at this point, the problem translates into the following. I have this function v of b, which is given by b squared times 10 minus b. And this function is defined from 0 to 10. So basically, I have to find the absolute extrema. So let's do that. So let's take the derivative. So we have that the derivative, I'm going to write it in this way with respect to b, with variable b, will be nothing else if you, so it will be 20b minus 3b squared. Or if you want to factor here some things, it will be b times 20 minus 3b. Okay, so that's the derivative. So the equation v prime of b equals 0 has solutions. And you'll see this will have two solutions. B equals 0 or b equals 20 over 3. And we have to retain these values. Well, if we retain the first one, there is nothing, b0, so that doesn't make any sense because the box would not exist. Just look at the picture, b cannot be 0. So we'll get rid of this guy, so we'll retain this guy here. So this guy here will be nothing else than just what we'll call the critical number, right? Okay. So this is the critical number. And now we like to evaluate. So this will be basically the maximum value, in fact. But let me be specific. This is the maximum value. And well, we would like to evaluate now v, when we evaluated b equals 20 over 3, this will give us, what else? B. It will be 4,000 over 27, which is approximately okay, so this would be 148.1. So at this point, the altitude, h, is 10 minus b, which is 10 over 3. And that's it. Because look at the problem. We're asked, what is the largest possible volume of such a box? Okay. All right, I think we have plenty of applications. There are more applications in my notes. You can look them up if you want. And now I like I said, I want to veer towards something else because this is very important as well. And this, like I said, it's an extremely important chapter. It's in fact one of my favorite topics in Calculus 1. And we call it, this is called the mean value theorem. And I'd like to, before I talk about the mean value theorem, I would like to talk about Rolle's theorem. So theorem, which is due to Rolle's theorem. And basically it says the following: suppose that a continuous, that f is continuous on a closed interval AB and differentiable on an open interval AB. Anyway, this is redundant because any differentiable, if I have a differentiable function, then it's continuous. We have seen that. All right. If we have this extra condition, and I'm going to just write it in this way, if f of a is the same as f of b, right? This is a very important condition. So if f of a is the same as f of b, then there exists at least one number, let's say c, and this c is between a and b, such that f prime of c is 0. And let me show you a picture of this. Let me just draw some things to see how this works. Let's just say we have here A and we have here B. Right. So in this case, as you can see, f prime of x is 0 for all throughout the whole open interval AB, right? Now let me draw you another picture so we can have the following situation. Let's just say we have the following scenario. So I have here A, and let me just say I have here B. And the function is like this, right? Let's just say it's like this. Oops, sorry about that. Okay, so let me draw it again. Okay. Right? So here, there are 2 points, here and here, right? Let me just, you see, there are 2 points, this guy here and this guy here, for which f prime of x is 0. So let's write that. So there are 2 points with f prime of x equals 0. And now let me draw another picture. When we have just one single point. Let me draw it here. And in this case, let me just say we have something like this. So here I have the A, here I have B. And let's just say the graph goes like this. Okay. And well, as you can see here on the, so in this case, there is only one point. One point such that f prime of x is 0. Well, as you can see, there are 3 scenarios for Rolle's theorem. It doesn't really matter that much. What you need to remember is from Rolle's theorem, it says that there is at least one number c, right? That's what you need to remember, at least one between a and b such that. And when I say here at least, I want to stress this one out. So at least one. If you look at this, in the first picture, all of them, so all the points x satisfy f prime of x equals 0. In the second scenario, there are two of them, so two. Indeed, there are more than just one, so at least one. And in the third scenario, there's exactly one, only 1 point, for which f prime of x equals 0. All right, so this is what Rolle's theorem is about. Now we're veering towards the most important theorem. So theorem, and we will call this the mean value theorem. This is one of the central objects of this course. And this is important for you to know. This is due to Lagrange. Let me mention this. Joseph Louis Lagrange. It's a French mathematician who lived in the 1700s. Well, you know, there is still a dispute. Well, he's French. Some Italians, they claim that it's Italian because his actual name was very Italian. It was Giuseppe Luigi Lagrangia. So you see the Italian version of Joseph Louis Lagrange. So anyway, officially he's a French mathematician and with many contributions in analysis, number theory, and so on. Well, I would say many contributions in mathematics. But among these very like I would say existential contributions in mathematics, there is this particular theorem, which we call nowadays the mean value theorem. And let me write it with red. And the mean value theorem has the following statement. So if f is continuous on the closed interval AB and differentiable on the open interval AB right, then there exists at least one number C between A and B such that we have the following. Let me write this with even a different color. Such that f of B minus f of A over B minus A, so this is the average value, is f, the derivative of f evaluated at this point C. So this is the mean value theorem. I want you to look at it for a bit. Like I said, it's one of the most important theorems in this course. So you see, I don't need any conditions for, so I just need that the function to be continuous on the closed interval AB and differentiable on the open interval AB. And then once we this is satisfied, we have this condition here. Well, as you can see, Rolle's theorem will follow immediately. So let me point out this remark. In fact, this is a much more general version of Rolle's theorem. So the mean value theorem, so I'm going to abbreviate it like this from the AMVT, so mean value theorem. Let me just write this here. So the mean value theorem implies Rolle's theorem. But not the other way around. Well, right? All right, now let's see an example. I'd like to show you an example. And I want you to see how we can apply the mean value theorem to solve some problems, right? So the example is the following. Find this the number C, which satisfies. So find all C which satisfy, many of them, the mean value theorem. So I will abbreviate the MVT. So the MVT for the following function for f of x equals x cubed plus x squared on the interval 1, 2. Okay. Okay. I want you to look at the theorem again. And now let's see. Now first we need to compute the derivative. So we have that f prime of x is equal to 3x squared plus 2x, right? Okay. So f prime of c is 3c squared plus 2c. And now, by the mean value theorem, right? So by applying the mean value theorem, we have that. So we apply on this interval 1, 2. Keep in mind this. So here the mean value theorem is applied on this interval. So we will have that f of 2 minus f of 1, everything over 2 minus 1 is the same as f prime of c, which in our case is 3c squared plus 2c. All right, and now let's compute this guy here. So this guy will be nothing else than f of 2 minus f of 1. And now f of 2 will be 8 plus 4. So f of 2 is 12 minus f of 1 is 2, which is 10, right? Now this will be equivalent with the following equation. So we obtain the quadratic equation. Um, 3c squared plus 2c minus 10 equals 0. And we would like to solve this, right? We can solve this equation. So with solutions, I remember the solutions were quite ugly. So the solutions were like something like solution C1 and C2. Let me, I'll leave them to you as an exercise to solve them. So it's -1, square root of 31 over 2. And the last, which is approximately, well, let's see, we'll see afterwards. And then the second one is -1 plus square root of 31 over 2. And now keep in mind that this, we would like to see if this guy will, if these numbers are in this interval in 1, 2. Keep in mind where, do not forget where the function is defined, on what interval the function is defined. That's very, very important. Okay, so let's see. C1 is -1, negative, oh my, that's negative. That definitely that's not going to be in 1, 2. And the last one, 31. Yes, the second one is good. So this one is good. That's beautiful. That's 1.5, something like that. Yeah. Okay. And that's the end of the story. So we found this. You see how useful the mean value theorem is? So basically, you can just find some C for which some numbers that satisfy the mean value theorem for some functions. Anyway, now let me mention 2 more theorems. And the first theorem that I would like to mention is the zero derivative theorem. And it says the following. So suppose that f is continuous, is a continuous function on the closed interval AB, right? And differentiable on the open interval AB. Okay. With this condition here, let me say f prime of x, so the derivative will be 0 for all x in AB, in this open interval. Then the function is constant on AB. Then the function is constant on AB. Okay. That's the first theorem. So if the derivative is 0, then the function is constant. So that's what you need to know. And now let's see the between two different. If we have two functions whose their derivatives are equal, what happens? What is the difference between those two functions? Well, the answer is quite clear. The functions will differ by a constant. So let's just call this. This will be called. Let's call it. How should I call it? Constant difference theorem. Let's say. And it says the following. So this time we'll deal with two functions. So suppose the functions f and g are continuous on the closed interval AB. Okay. And differentiable on the open interval AB. Then, if we have that, okay, let me write it in this way. Then if f prime of x is the same as g prime of x, right? If the derivative of a function is equal with the derivative of another function, then, okay, I would like to, okay, for all x in the interval AB, then there exists a constant let's just call it C, such that, guess what? Their difference will differ by just this constant C. So such that f of C is the same as g of C plus constant C for all x in the closed interval AB. Okay, so this is what's going to happen, right? Okay, so these are the two theorems that, so as you can see in this, let me point out something. The slope of at each point of f and g are equal. So let me point out this remark. So this means that since the derivative, since f prime of x is equal to g prime of x, so since they're the derivative of these two functions are equal, it follows that the slope at each point of f of x and g of x are equal. Slopes are equal. In fact, we will have the following scenario. Let me just draw a picture so that you can see it better. So we'll have something like this. Let me just say this is f. So this f is nothing other than just g of x plus a constant. So is lifted. So and the same thing happens here. Oops, sorry about that. Basically, this is g of x. So it's lifted by a constant. So that's the scenario. It's pretty similar, right? Right. Okay. I think I'm going to stop here. This is just the beginning. So this is the first lecture in this chapter 4. As you can see, we talked about qualitative properties of differentiable functions. And in fact, next time in the next video lecture, I'll be talking about how to use these derivatives to sketch the graph of a function. And then afterwards, I will use this curve sketching with asymptotes. And I will also talk about limits involving infinity. And then afterwards, there will be a method of computing limits of all kinds using this so-called L'Hopital rule. All right, guys, thank you very much. I'm going to stop here. And well, there will be more videos coming out. So stay tuned. Bye-bye.